Theorem is a concept in computer science that explains the trade-offs between consistency, availability, and partition tolerance in distributed systems. Consistency refers to the property of a system where all nodes have a consistent view of the data. It means all clients see the same data at the same time, no matter which node they connect to. Availability refers to the ability of a system to respond to requests from users at all times. Partition tolerance refers to the ability of a system to continue operating even if there is a network partition. But what is a network partition? A network partition happens when nodes in a distributed system are unable to communicate with each other due to network failures. When there is a network partition, a system must choose between consistency and availability. If the system prioritizes consistency, it may become unavailable until the partition is resolved. If the system prioritizes availability, it may allow updates to the data. This could result in data inconsistencies until the partition is resolved. Now let's go through a concrete example. Let's say we have a tiny bank with two ATMs connected over the network. The ATM supports three operations: deposit, withdrawal, and check balance. No matter what happens, the balance should never go below zero. There is no central database in this bank to keep the account balance. It is stored on both ATMs. When a customer uses an ATM, the balance is updated on both ATMs over the network. This ensures that the ATMs have a consistent view of the account balance. If there is a network partition and the ATMs are unable to communicate with each other, the system must choose between consistency and availability. If the bank prioritizes consistency, the ATM may refuse to process deposits or withdrawals until the partition is resolved. This ensures that the balance remains consistent, but the system is unavailable to customers. If the bank prioritizes availability, the ATM may allow deposits and withdrawals to occur, but the balance may become inconsistent until the partition is resolved. When there is a network partition, the customer could withdraw the entire balance from both ATMs. When the network comes back online, the inconsistency is resolved and now the balance is negative. That is not good. Now let's go through another example and see how a social media platform could apply the CAP theorem. During a network partition, if two users are commenting on the same post at the same time, one user's comment may not be visible to the other users until the partition is resolved. Alternatively, if the platform prioritizes consistency, the commenting feature may be unavailable to users until the partition is resolved. For a social network, it is often acceptable to prioritize availability at the cost of users seeing slightly different views some of the time. The CAP theorem may sound very simple, but the real world is messy. As with many things in software engineering, this is all about trade-offs, and the choices are not always so black and white. The CAP theorem assumes 100% availability or 100% consistency. In the real world, there are degrees of consistency and availability that distributed system designers must carefully consider. This is where the simplistic model of the CAP theorem could be misleading. Now back to the bank example. During a network partition, the ATM could allow only balance inquiries to be processed, while deposits and withdrawals are blocked. Alternatively, the bank could implement a hybrid approach. For example, the ATM could allow balance inquiries and small withdrawals to be processed during a partition, but block large withdrawals or deposits until the partition is resolved. It is worth noting that in the real world, reconciliation after a network partition could get very messy. The bank example above is simple to reconcile. In real life, the data structures involved could be complex and challenging to reconcile. A good example of a complex data structure is Google Docs. Resolving conflicting updates could be tricky. So is the CAP theorem useful? Yes, it is a useful tool to help us think through the high-level trade-offs to consider when there is a network partition. This is a good starting point, but it does not provide a complete picture of the trade-offs to consider when designing a well-rounded distributed system. Specifically, when the system is operating normally without a network failure, which is most of the time, there is an entire set of instruments
Today we would talk about what C, A and P in CAP theorem stand for, why it works the way it does, and what does CAP theorem mean in the modern ecosystem. I was fortunate to see tech at scale at Facebook and was able to design products that served millions of queries per second and billions of users. I'm here to share a few of those learnings with you. If you like the content, please like the video and subscribe to the channel.
Alright, so let's first look at why do we even need to learn CAP theorem. CAP theorem is one of the most basic principles of distributed storage. So if at all you think about building or working on distributed systems in the future, CAP theorem is a must-have, must-know. So that's why you need to learn CAP theorem. Now before I get into explaining CAP theorem, and I would try to do that with using as simple example as possible, I want to give credit to Kaushik, whose blog I have borrowed a few ideas from. So thank you, Kaushik, for coming up with a very, very innovative example. So let's get to it, right? So to elaborate CAP theorem, I'll take example of a real world example of let's say you. Imagine I am an entrepreneur. I'm looking for ideas and I feel, you know what, like people need reminders. Let's build a service that just stores reminders, right? Which is, I get this very premium number. Imagine I name my company as ABCD and I get this very premium number which is 1234, 1234. People could just call me on 1234, 1234 and they can tell me what they want to remember. And then when they call me back, I tell them what they wanted to remember and then things work. It seems to me that this is a great idea. So what I do is I set up this line, I sit in the office. Imagine this is me, forgive my drawing. Imagine I sit in the office. Every time somebody tells me, let's say I got a call from X and X says, hey, please remember that I have a flight tomorrow at 9 p.m. I say, great. Next time they call and they ask me, tell me what I wanted you to remember, and then I tell them, you know what, do you have a flight tomorrow at 9 p.m. And then this seems great. I charge people very nominal amount of money to store this information and service takes off. Everybody needs this. There's a big market. Everybody starts using it. And then I start to hit the problem. And you'll notice most systems, they start to hit the problem when they hit scale. Then I realize that I'm getting a lot of calls and I'm not enough to address all of those calls myself. So then I start to think, and then I think, sure, let me get my wife also involved. So now this number actually has me and my wife, both of us sit with our diaries where the call gets routed to either one of us, whoever is free. And when I get a call, I just very quickly, if the person is asking me to take a reminder, I just take down that reminder, right? And when the person calls me back, I respond back to the reminder. Great. I have suddenly now doubled my capacity. If I was able to take 1,000 requests in a day before, now I can take 2,000 requests because I have my wife to help me as well. Very soon I got my first unhappy customer. Mr. X calls me one day and says, hey, can you please remind me when is my flight? And I look through my diary and I realize I don't have an entry corresponding to Mr. X. And I tell Mr. X, hey, look, I don't have an entry corresponding to you. Mr. X seems very disappointed, very angry, and then disconnects the call. Now I start to think, what might have happened? Either Mr. X was delusional, or maybe there was a fault at my end. And then I see that there might have been a problem. It is possible when Mr. X wanted to store their reminder, they might have called my wife. And my wife would have stored this entry that, hey, X wants a reminder for a flight at 7 p.m. tomorrow. However, that entry is not with me because that call never came to me. However, when X wanted to understand when their flight was, they ended up calling me instead of my wife because they don't know. They only know this number 1234, 1234. And I don't have that entry. And this is why X is very unhappy. This is what is called as consistency problem, data consistency problem, which is an end consumer might have stored some data with me, and when they ask me back, there is no guarantee that they will get the data back because it depends on where the request comes to. If the request comes to my wife, they'll get their data back. If the request comes to me, they'll not get the data back if my wife's diary has that entry. This is a big problem. If not solved, my company will die. So I start to think, and I come up with a solution. I say, hey, look, here is what we could do. When X calls me to say that please note down that I have a flight tomorrow at, imagine, 6 p.m. I'll note it down in my diary. I'll also tell my wife to note down this entry, which is also that tomorrow 6 p.m. flight. And only when both of us have written the entry in my diary, in their own diaries, then I return success. Then I tell Mr. X, I have noted down your entry. That way there is guarantee that both of our diaries, my diary and my wife's diary, they'll have the exact same entries. Consistency of data. They'll have the exact same entries. And great, my consistency problem is solved. Now when X calls any one of us, we can respond back with the right data points. Things were going great. One day I again start to face a problem. One day my wife calls in sick. She's not keeping well, so she's not in the office. What that means is that my wife for the time being is gone. For a day is gone. And at that very moment, another gentleman Y calls me and tells me to note down an entry. I say, okay, sure, what's your entry? And they tell me, you know what, I have a flight tomorrow at 3 p.m. I say, great, let me note it down. Let me, by the way, also go and tell my wife to note it down. Oh, by the way, my wife is not here. She can't note it down. And therefore, I'll have to tell Y that, hey, I can't note down your request. Your request actually has failed, which means for the entire day, I can't take in any new requests. That is a availability problem, which is my system is not available to take all kind of write requests. In the case of software systems, for example, like Facebook, you could think of Facebook saying that for an entire day or for an hour or for a few minutes, you can't make any new posts or you can't post any new photos on Facebook. That is an availability problem. So again, I'm very stressed. What do? I don't want my business to fail. So I think and I come up with another solution. I say, you know what? When my wife is not here, so I have my diary. And imagine my wife is not here, so I have written a bunch of entries. This new day comes. Whatever entries I get, Mr. X says to note down something, I'll note it down. When Mr. Y says to note down something, I'll note it down. And when my wife returns back, because I want both of our diaries to be identical, I tell her, look, you'll not take up any phone calls till you have noted down all of the additional entries that I made in the previous day. Or if she was gone for last 2 days, then in the previous 2 days. So you first note down all of the additional entries and then you start taking calls. And then my problem is solved. Now because if X calls me and says that please note down that I have a flight tomorrow at 8 p.m. Even if my wife is not in the office, I can still note down the entry and therefore I'm still available. Since my wife will come back and she'll actually catch up with whatever new entries are there in my diaries before answering any phone call. So we're also consistent, which is great. Things are going super good. And then comes another problem. One day, me and my wife, we both have fight and we stop talking to each other. So imagine I get a phone call, X says, hey look, please note down I have a flight tomorrow at 9 p.m. I can't note it down because I'm not able to talk to my wife. And if I note it down, then and tell X that, hey look, I have noted down your entry, then my system becomes inconsistent. Right? Because my diary has now different entries, my wife has different entries, and she's still taking calls. So when this network partition happens, where I'm not able to talk to my wife or other systems, then I have to make a choice. Do I want to stay consistent or do I want to stay available? If I want to stay consistent, then if Mr. X calls me and says, please note down the entry, I will have to say, sorry, I can't. My system is down. It's not accepting any new write requests. If I want to stay available, then I can take down the entry, but then I become inconsistent. So if I choose consistency, then I become unavailable. If I choose availability, then I become inconsistent. And that is exactly the CAP's theorem. CAP's theorem says that if you have consistency, if you have availability, and if you have partition tolerance, then at a time you can only guarantee 2 out of these. You can't promise all 3 at the same time, which means when this network partition happens, I would have to choose between consistency and availability. I can't have both. That's the CAP theorem. Now I have 2 bonuses to add here. Most systems that are available and partition tolerant, which is called AP, A for availability, P for partitioning, C for consistency, right? Most systems that are AP can still make sure that they become eventually consistent. What does that mean? That means eventually my and my wife's diary, they have same entries. How do I make sure of that? Whenever we start talking again, we can exchange notes. Or maybe just imagine that there's a clerk here that I've hired who just takes up all of the new entries in the last 1 hour, tells me what those entries were, so I take those down. Also, by the way, asks me what were the entries that I made in the last 1 hour, goes back to my wife and tells, here are the new entries that were made in the last 1 hour. So there might be periods in between that I was inconsistent, but eventually we become consistent. So that is eventually consistency. There is one more extension to CAP theorem that was done very recently, actually not very recently, about 10 years back, which is called as PACELC theorem. And what this theorem states is that, hey, look, when network partition happens, when my systems can't talk to each other, then sure, you have to choose between availability or consistency. You can't have both. However, there are going to be cases when my systems can talk to each other, which means there is no network partition, which is else. So else, I have to choose between latency or consistency. I can't have both. If you notice, when I made this decision that to stay consistent, I will make sure that on every single call, I will make sure my wife also notes down the entry, and only then I return success. Then I'm actually waiting for my wife to note down that entry. My wife could be doing something else at that time. My wife could be answering some other call, and in that case, the entire request might end up taking a lot of time. So the latency could become high because I want consistency. However, if I was willing to let go of consistency, which is I wanted to say that, hey, look, I'll just note it down, and maybe my wife could probably catch up later on, then latency could stay really low. So then you would actually have a balance between latency and consistency when there is no network partition. So that's what PACELC theorem is, which is just an extension to the CAP theorem, because CAP theorem does not talk about latency. I hope that made sense to you, and I hope that was helpful. This CAP theorem is one of the most basic and one of the most useful theorems you'll come across when designing distributed systems. I'll keep doing more videos like this.
CAP is an acronym which stands for consistency, availability, and partition tolerance. It was proposed by Eric Brewer, and it says that any distributed system can only guarantee two of these three properties at a time. So no distributed system can have all these three at the same time. Before we learn more about the CAP theorem and we discuss these three properties in detail, let's make sure that we know what is a distributed system. A distributed system is any system whose state is split across two or more systems. So here we have an example of an order management system. So let's say that the user places an order, and then the order service connects to the loyalty API and gives the user some points, the loyalty points for their transaction, and then the user can check with the loyalty API to get the number of points that they have received from the orders that they have placed. Distributed systems is not only specific to the APIs and services, it can also apply to the storage and databases as well. So for example, a database might be consisting of several nodes. So all these nodes are connected together to form one database system. So this is an example of a distributed system as well. So this was just a brief example of what is a distributed system. I'll be covering them in much more detail in a separate video discussing what are the distributed systems, why were they needed, and some examples and so on. For now, let's take an example of a simple payment system, which is a distributed system consisting of two servers, S1 and S2. Both of these servers contain a balance of the user, and the client can request either of these servers to get the available balance that they have, withdraw or deposit into the account. We will now see how the properties which are consistency, availability, and partition tolerance apply to this payment system. Let's say that the user makes a request to server 1 to update the balance to be $90. So they withdraw $10 from server 1. Server 1 is going to update the balance to be $90. It is going to make the request to server 2 to update the balance to be $90 there as well. Get the acknowledgement from that and acknowledge the client that the balance has been updated in both the systems. Now when the user will make a request to server 2 to get the balance that they have, they will get the $90, which is the correct user balance. Now in this case, both the servers S1 and S2 have the correct balance of the user. We will say that the system is in a consistent state. Let's take an example of the inconsistent system. I have reverted the amounts on both the servers to be $100 again. Now let's say that the client makes a call to S1 to withdraw $10. So S1 is going to update the balance to be $90. Now let's say that the S1 does not notify the S2 about the balance change and just acknowledges to the client that the balance has been updated. Now if the client makes a call to S2 to get the available balance that they have, they will get $100. But the actual balance of the user is $90 and not the $100. So in this case we would say that our system is in inconsistent state. So this is what the consistency is about. All the nodes of a distributed system should have the consistent data. Next we have availability. Availability is quite simple, and it means that if the node is not crashed and user makes a call to the node cannot ignore the request. It must fulfill the operation that the user is requesting. We will see an example of the availability in a minute when we look at the proof of CAP theorem. So next we have partition tolerance. Partition tolerance means that if the partition happens within a distributed system, the system must continue to operate properly. So what do we mean by a partition? If we look at the same payment system that we have built, so if the connection between S2 and S1 cannot be established, maybe because of the network issues or maybe because S2 is down, so in this case we would say that our system is in a partition state. So partition tolerance property just means that if the partition happens within a system, the system must continue to operate properly. Alright, so now that we know what is consistency, availability and partition tolerance, let's look at the proof of the CAP theorem, which means that none of these three can exist all at the same time. A system can only guarantee two of these three properties at the same time. I will take the same example of the payment system that we were looking at, where we have two servers containing the balance of the user, and user can request either of these servers to withdraw or deposit the amount. Let's say that the partition happens and S1 is not able to connect to S2. Now a user makes a call to S1 to update the balance. S1 is going to update the balance to be $90, but S1 is not going to call S2 because the connection is not there. And when the user will make the call to S2 to get the updated balance of the user, they will get a different amount from the S1, so $100 instead of 90. So in this case, if we look at the three properties that we have, our system does support availability because both the nodes are replying to the requests, and partition tolerance is also there because even if the partition is there, our system does continue to work properly. But the consistency is not there because the balance across both the nodes is not the same. Alright, so let's see how we can fix this issue of the consistency. I will revert the balances of both the servers to be $100 again. Let's say that the partition is still there. Now if the customer makes a call to S1 to withdraw some amount, the server 1 is going to check with S2 if it can connect to that. It will see that it cannot connect to S2, so it is going to reject the request, saying, because I can't connect to S2, I can't let the withdrawal happen because this will bring the system in an inconsistent state. So now in this case, if the customer makes a call to S1 or S2 to get the available balance, the balance is always going to be in a consistent state. So now if you look at this implementation of the system, our system does support consistency. And it also supports the partition tolerance because under the partition, our system is still operating. But if we look at the availability, we have lost it because even if the server 1 is available and it can accept the requests, it is not fulfilling the requests because fulfilling a request would let the system be in an inconsistent state. And as you can see from this implementation that while optimizing for consistency, we had to lose the availability. And in the last example, if we had to focus on the availability, we had to compromise on the consistency of the system. Let's say that we want both the consistency and the availability. Let's look at the example in that case. So if the user makes a request to S1 to update the balance, so S1 will become $90. S1 will make a call to the S2. S2 now also has the $90. And now if the user requests either S1 or S2 to get the available balance, it is going to get $90. So in this case, our system does have consistency and it does have availability because both the servers are available all the time. Now if we inject the partition into this system, we end up in one of the past two cases. So either the system becomes inconsistent or we have to compromise on the availability for system to be in a consistent state. So we can say that our system is no longer partition tolerant when the partition happens. Normally when designing distributed systems, it is always assumed that the partition is always going to happen. So our system must be partition tolerant. And the choice is always between the consistency and the availability. And that is all what the CAP theorem is about. I hope you enjoyed this lesson.